For nearly a century, our understanding of the universe has rested on a single mathematical framework, the Standard Model of Cosmology. It has successfully predicted everything from galaxy distribution to the abundance of hydrogen, operating like a flawless engine where every equation locks cleanly together. But that engine is breaking down. Nobel laureate Adam Riess, a physicist who spent his career measuring how fast the cosmos is flying apart, has looked at the incoming data and delivered a blunt assessment. We have misunderstood the universe. The problem starts with a single metric called the Hubble constant, which tracks the exact rate at which the universe is expanding right now. You would expect two distinct, highly precise measurement techniques to arrive at the exact same speed. Instead, they are producing a stubborn, irreconcilable gap. One technique maps the cosmic microwave background from the Big Bang and runs the equations forward, predicting an expansion rate of 67 points. But Adam Riess's team measures the present universe directly, using pulsating stars and supernovae. Their expansion rate lands firmly at 73. In a field where measurements are accurate to within 1%, an 8 or 9% gap is an enormous paradox. If the universe is expanding that much faster than the model predicts, the cosmos is a billion years younger than we thought. The distances between galaxy clusters shift significantly, and the window for the first heavy elements to forge moves to a different epoch. Initially, astronomers assumed someone had just made a math error. The leading theory was a phenomenon called stellar crowding. The specific stars used to calculate that higher expansion rate live in the dense, dusty disks of young galaxies. Scientists figured our telescope lenses were simply blending the light of nearby stars together, making them appear brighter and artificially inflating the calculated speed. The controversial data came from observations made by the Hubble Space Telescope, which, despite its immense power, has limitations when staring through deep cosmic dust. The astrophysics community collectively held its breath, expecting that a new, more sensitive instrument would eventually pierce through that interference, resolve the individual stars, and bring the math back into alignment. The integrity of our entire cosmological framework was left resting on a single fragile hope, that our older cameras were just slightly out of focus. That hope was put to the test when the James Webb Space Telescope launched. With its massive gold-plated mirrors and infrared sensitivity, Webb was designed to be the ultimate arbiter in this debate. Astronomers pointed its lenses at the exact same pulsating stars Hubble had measured, expecting Webb's sharper vision to expose the blended light and deflate the tension. That did not happen. Webb confirmed Hubble's numbers almost exactly. The stars looked the same, the distances held steady, and the expansion rate stayed locked at 73. Measurement error was entirely ruled out. To complicate things further, astronomer Wendy Friedman ran an independent analysis using completely different types of stars. Her results landed around 70 kilometers per second, suggesting that the very distance ladder methodology astronomers have relied on for a century might possess its own hidden structural flaws. With camera glitches firmly eliminated, we are left with a direct contradiction. The expansion rate we measure in the local universe cannot be reconciled with the physics governing the early universe without changing the model itself. And the tension over expansion is only the first fracture. Almost as soon as Webb turned on, it delivered a second blow, capturing images of fully formed, impossibly massive galaxies existing just 500 million years after the Big Bang. As this diagram demonstrates, part of the mystery was an optical illusion. Researchers identified a phenomenon called little red dots, where supermassive black holes rapidly devoured gas, radiating extreme heat and light. This glare acted like a flashlight taped to a candle, artificially inflating the apparent mass of the host galaxy. But even after filtering out those glowing black holes, roughly twice as many massive infant galaxies remain as the math allows. Watch the count on this chart. These early structures are still pushing right past the absolute limit of what the standard model permits. To build galaxies that heavy, that quickly, nearly all available raw material in a dark matter halo would have to convert into stars with a 100% efficiency. Physics simply does not support that kind of conversion rate. It is a direct violation of the cosmic timeline. As if that wasn't enough, Researchers recently found that many of Webb's young galaxies are strikingly stretched out into shapes resembling cosmic cigars. These elongated profiles directly contradict the long-held cold dark matter theory, which predicts that early structures should form in tight, chaotic clumps. Instead, these prolate shapes align perfectly with alternative theories, like warm or wave dark matter, where particles behave as long, smooth streams rather than dense, static blocks. This echoes a quieter, ongoing issue known as the S8 tension. When astronomers directly measure the distribution of mass across space, they consistently find that the universe is slightly smoother and less tightly clustered than the model requires. But you cannot simply swap out the behavior of dark matter to solve the problem. It is the primary scaffolding of the cosmos. If you alter how that unseen gravity behaves, the ripples of that change will tear through and invalidate nearly every other prediction the standard model successfully makes. So, how do we reconcile a universe that refuses to follow its own rules? The leading hypothetical solution is something called early dark energy. Imagine a temporary, intense burst of expansion occurring in the first few 100,000 years after the Big Bang, before quickly vanishing. That early, unexpected kick would shift the conditions of the infant universe just enough to cleanly align the old mathematical predictions with the modern measurements we see from Webb. While no one has yet detected early dark energy, its proposal represents the current state of astrophysics. The field is operating at the edge of its own understanding, where every failed prediction serves as a pointer toward a hidden layer of physics we have yet to name. A whole new generation of instruments, like the Nancy Grace Roman and Euclid Space Telescopes, are launching with the specific mission of mapping this geometry and hunting down the missing physics hidden in the cosmic dark ages. We are living inside a contradiction, with the most precisely measured universe in history telling us two different things at once. This friction between the beginning and now suggests our current map is missing an essential coordinate, and the next version will be stranger and more profound than the one we have outgrown.